Okay, I'm sorry.
Oh, it's okay, no problem.
You can see my screen?
Oh yeah, I can see it.
Okay,
so
perfect.
I'll give you 15 minutes. Okay, so when
Yes.
you have 3 minutes left, I'll tell you, okay?
Okay, thank you very much. Okay, my name is Joxara. Hello, everybody. I am PhD student in the International Institute of Physics. Many thanks to the organizer PASCOS event for accepting my submission. Today, I will talk about implication of the monoanomalous magnetic moment for 331 models. This work is based on this archive here in collaboration with Alvaro de Jesus, Sergei Kovalenko, Carlos Pires, and my advisor, Farinaldo Queiroz, from these universities from Chile and Brazil. The summary in this talk is the following. First, I will introduce the monoanomalous magnetic moment. Then I will explain the 331 models and contribution to G-2 from these models. And finally, I hide the results and conclusions. First, I will introduce the monoanomalous magnetic moment. You know the direct equation in the tree level. The mode magnetic moment is described for this equation. Is proportional to the ferromagnetic ratio, the letter G here. And in the tree level, this value is 2. But in quantum correction, the rate deviation of this value is different of 2, it's different to 2. And the mode anomalous magnetic moment, in this way, is defined for this equation. And this value here corresponds to the theoretical value to the G-2 of the standard model reduced to monoanomalous magnetic moment. The main contribution to the standard model, you can see here, the first order quantum electrodynamic, the lowest order weak are hadronic effects. In a loop, you can see the gauge boson photons, C and W, and hadronic effects. But now there are discrepancies to the theoretical value and the measurements. And you can see here some discrepancies of these values. In our work, we take this value here, the current discrepancies, taken from the particle data group. For these discrepancies, it's interesting to analyze new particles in a loop that contribute to G-2. For this way, in our work, we explore new models, new contribution, and new particles in a loop that contribute to G-2 for some models in this gauge symmetry 331. The models analyzed in this work are the following: the 331 models, minimal 331, 331 with right-handed neutrino, 331 with neutral heavy leptons, economical 331, and 331 with exotic leptons. The charged operator of these models is given for this equation, where the lambda 3 and lambda 8 and I correspond to the generators of this model, of this group, I'm sorry, and the factor alpha contain different values dependent of the model. These models are very important in beyond standard model because explain new physics, for instance, neutrino masses, dark matter, flavor violation, collider physics, etc. The scalar sector of the 331 models contain 2 or 3 scalar triplets. In these models, all models contain 3 scalar triplets, but the economical models only contain 2 scalar triplets. In this sector, there are 2 spontaneous symmetry breaking. The first spontaneous symmetry breaking contains the vacuum expectation value, the key, and this value is the order to electron volts. The first spontaneous symmetry breaking take us to the electroweak group to the standard model, And the second spontaneous symmetry breaking is the same way to the spontaneous symmetry breaking known on the standard model. The fermionic sector is described for the leptonic triplet because it's the representation of the 3-1 models. The first two components in the models in the leptonic triplet are the same particles to the standard model, and the third component change depending of the model. For instance, in the minimal model, you can see the conjugate charged lepton in 3-1 RHN and economical model appear the right-handed neutrino appear in the third component here. The 3-1 with neutral heavy lepton, this particle is the third component, and there are the singlet too. All leptonic triplets correspond to the 3 families. And finally, the 3-1 with exotic leptons contain charged and neutral exotic leptons in the third component for 3 leptonic triplets. There are two additional leptonic triplets, and the particles are the exotic leptons too. The point important here is in the model appear new leptons beyond standard model and new scalar fields confront to the triplet scalars. Also, for the gauge symmetry, there are new gauge boson. Now, for instance, W prime and C prime, very important in collider physics. And there is the U++. This gauge boson only appear in the minimal 3-1. In this way, these gauge bosons interact with the leptons of the new leptons 2 and standard model leptons 2, and the scalar fields interact in a loop with the leptons. In this way, the main contribution to G-2 in our work is displayed in these diagrams here. In a loop appear as neutral and charged scalar fields, and new gauge boson U-, C prime, W prime, Q0, and Q-. These gauge boson appear in the 3-1 exotic leptons. And the important here is you can see the interactions with the scalar fields and gauge boson with the leptons in our models. Okay, the mathematical numerical codes available in this link here corresponding to G-, the contribution to G-2 for 3-1 models. The general analytical expressions to G-2 you can find in this reference here, that you can find new physics contribution to G-2 and lepton flavor violation. The results in our work you can see in these plots. You can see the black line here in all plots that correspond to the total contribution to G-2. In this way, we obtain the contribution to the scalar fields and gauge boson in a loop with the lepton particles, and obtain the total contribution H model to the G-2. The green bands here correspond to the current discrepancies, the up or down, and the red bounds are the projected discrepancies taken in our work, approximately 5 sigma. In all models, we got the lower bounds in the current and projected discrepancies here for this value, background expectation value. And in this way, we obtained the masses of the gauge bosons, C prime and W prime, because these masses are proportional to this background expectation value. In our work, we obtained the lower bounds to the masses of the gauge boson C prime and W prime, but the masses are smaller than the lower bounds to the LAC. In this way, none of the five models investigated here can accommodate the G-2, taking into account the bounds in collider physics. In this way, we made a solution for accommodate the G-2 in the 331 models. We made the standard version to 331 with neutral Hebel leptons, and to add in the inert scalar triplet. The interaction that contribute to the G-2 in this model is described by this Lagrangian here, and the contribution, the black line in the plot, you can see the lower bounds here is largest to the lower bound to the LAC for the vacuum expectation value. In this way, we obtained the solution to the solution for accommodating the G-2 on the 331 models. In this case, the 331 model is necessary to extend the 331 models. Our conclusions in our work is the following. We conclude that none of the five models investigated here can accommodate the anomaly. We derived robust and complementary 1 sigma lower mass bounds on the masses of the new gauge bosons, namely the C prime and W prime boson that contribute to G-2, assuming the anomaly is otherwise resolved, and the 331 models must be extended to explain the anomaly observed in the G-2, and we present a plausible station to 331 with neutral Hebel lepton model with features and inert scalar triplet. For any question or comments, you can write to this email. Thank you so much for your attention.
Thank you. Thank you for the nice talk. Yeah.
You're welcome.
So do you have any question? Oksana, would you go to page 8?
Yes, I am a student of the PhD.
Yeah. Okay. Would you go to your page 8, your presentation?
I'm sorry?
I have a question. So would you go to your page 8?
My page
8.
8. Okay, page 8. I'm sorry.
It's okay.
Yes.
That was your main results, right? Here. Yeah, here.
Okay. The main contribution to the G-2 in these plots.
Yeah, but I don't understand. So,
okay.
So green lines, right?
Okay.
Two green, right?
I'm sorry?
You have 2 green lines. You can hear it? Okay, let me check.
Okay, the green lines correspond to the up or down. In this way, 2061 plus 78 are minus 78. Is the up or down, the current discrepancies.
Okay, so my question is, okay. My question is, let's look at the first one, minimal 331. Then actually green lines, there are 2 green lines, right? So you can explain this muon G-2 when your V chi is about 1 TeV, right?
1 TeV, yes. Here's the contribution here corresponds to the value, the contribution to the...
Yeah, but in conclusion, you said the model is excluded.
Yes, the model
Why
is excluded because we obtained the lower bound of this vacuum expectation value. The vacuum expectation, the masses of the gauge boson in all models depend of this vacuum. And we made the comparison with the masses, the lower bounds, the masses in
I see.
physics.
So you cannot explain both. Okay,
yes.
Okay, I see. Okay.
I'm sorry.
Thank you. Any other question? Okay, then let's thank the speaker again.
Okay, thank you very much.
Thank you. Then would you stop sharing? Okay, our second speaker is Julia. Hello, Julia.
Yes, hello.
Hello. Would you share your screen?
Yes.
Okay, great. So I'll give you 15 minutes.
Yeah.
Okay. Please start.
Okay. So thanks a lot for letting me talk today to you about leptonic flavor models. So neutrinos are the ideal laboratory to test symmetries of nature. For example, we can test with neutrinos if CP is violated in the lepton sector and by how much, by measuring the Yards-Cook invariant in neutrino oscillation experiments. We can also test if the individual lepton numbers are conserved, and we know from neutrino oscillations that they are not conserved. However, so far, it seems like total lepton number is conserved. We are looking for this in neutrino-style beta decay experiments, and finding a violation of lepton number is also tightly linked to the question of the nature of the neutrino masses, Dirac versus Majorana neutrinos. So by observing total lepton number violation, we also obtain insights into neutrino mass generation mechanism. But what I'm going to talk about today is that neutrinos are also an ideal laboratory to test flavor symmetries. So the leptonic mixing matrix is parameterized as a 3x3 matrix with three angles, one CP violating phase and two CP violating Majorana phases, which are only physical if total lepton number is violated. So I'm going to parameterize the P-S matrix as a series of the three rotations, although also other parameterizations exist. We already have a good and consistent knowledge about the leptonic mixing angles. We know that one of the mixing angles is close to maximal, theta 2, 3. We know that one of the other angles, theta 1, 2, is also very large with around 32 degrees. And the smallest mixing angle, theta 1, 3, has a value of around 8.5 degrees. We also have some measurements of the CP violating phase delta. However, currently the 3 sigma allowed range of delta is very big, such that basically the whole range of delta is still in a good agreement with the experiments. From the measurement of the mixing angles, we see that the leptonic mixing pattern is very different from the mixing for the quarks in the CKM matrix. For the leptons, the P-S matrix, the mixing is very off-diagonal. We observe large flavor mixing for the leptons, whereas in the quark sector, the mixing matrix is close to diagonal. We have very little flavor mixing in the quark sector. Now questions will arise, why is the leptonic mixing matrix so off-diagonal? Why is it so different compared to the mixing matrix of the quarks? And maybe is there some underlying symmetry or reason why the leptonic mixing matrix looks how it looks? And then finally, how can we probe this? So the most promising way to probe and disentangle the models which have been put forward to explain the leptonic mixing matrix is via precision measurement of the mixing parameters. So we should really make it the goal of the upcoming neutrino oscillation experiments to reach the sensitivities to probe flavor models. It turns out that the most predictive models not only predict the mixing angles, but they also predict correlations among the mixing parameters, and these are leptonic sum rules. There are two types of sum rules in the literature. There are mixing sum rules, which connect the leptonic mixing angles and the CP violating phase to each other, and these mixing sum rules can be tested at oscillation experiments. There is another type of sum rules, mass sum rules, which relate the three complex neutrino mass eigenvalues to each other, and these can be tested at neutrino star beta decay experiments and experiments sensitive to the absolute neutrino mass scale. Recently, a new approach to model building and to flavor symmetries has been put forward. And in this approach, the leptonic mixing matrix can be parameterized by two parameters only, an angle and a phase. This means that the four parameters in the PM&S matrix can be parameterized by only two free parameters. This means that there are correlations between the parameters in the PM&S matrix. This means that some rules will arise in models which have these modular symmetries. And together with my collaborator, Martin Spinrath, we investigated these leptonic sum rules in these models with modular symmetries end of last year in this publication, which is also published in JHAP. So we surveyed over 70 models, and 5 of these models had this maximal amount of correlations. We found that the 4 mixing parameters can be described by only 2 free parameters. And I show an example here. We see that that θ12 and θ13 both only depend on this free parameter theta. We see that θ23 and the CP violating phase additionally depend on this free model parameter phi. This example is very specific to this model from this authors shown here. However, the dependencies that two of the PM&S parameters θ12 and θ13 only depend on one of the model parameters, whereas θ23 and delta additionally depend on the phase. This is the same in all the models we found. So to obtain the predicted regions of the PM&S parameters, we determined the 3 sigma regions for the model parameters theta and phi from the chi-squared profile of the mixing parameters of the global fit. And in the upper plot, I show you the predicted values of θ12 and θ13 in the models we surveyed. The black star is the current best fit point from global fits. And the colored lines and stars, these are the best fit point of the models. We see that all of the model predictions deviate from the best fit point of θ12. In fact, sum rule 1 in blue predicts a value of θ12, which is very close to the upper 3 sigma bound of θ12. This means precision measurements of this angle θ12 can rule out many of these models. And in fact, the upcoming reactor long baseline experiment, Juno, will measure θ12 with a very good precision, as shown here in this lower plot, which means that Juno in the future will be able to thoroughly test these models and potentially rule out many of them. Moving on to θ23 and delta. Here I show again the predictions of the models with the black star, the global best fit point, and the colored stars, the best fit point in the models. We see that θ12 maximal corresponds to only this point here, which has delta equal to 3 pi over 2. Additionally, CP conserving values for delta, meaning delta equal to 0 or pi, are not favored in these models. In fact, if delta is equal to pi, it also means that θ23 is larger than maximal. However, the precision needed to disentangle, the precision in the measurements of delta and θ23 needed to disentangle these models depends on the true value of the mixing parameters. We see that sum rule 4 and sum rule 1 have very similar predictions, and which are also different from the predictions of sum rule 2 and sum rule 3. However, these are very interesting correlations to test with future oscillation experiments. Oscillation experiments are not sensitive to all neutrino parameters, they are not sensitive to the Majorana phases. However, there's a different type of sum rule, the mass sum rule, which includes the Majorana phases and predict values for them. So again, mass sum rules connect the three complex neutrino masses to each other and lead to constraints on the absolute neutrino mass scale, the observable in neutrino double beta decay, MEE, and sometimes also the mass ordering. Mass sum rules can be parameterized like this. So it's a coefficient f, an exponent of the complex mass, and then alpha 1, alpha 2 are the Majorana phases. We can visualize the sum rule as a triangle in the complex plane, and only if the triangle closes, the sum rule can be fulfilled. Previously, models with constant coefficients f1 and f2 have been studied in the literature. However, it turns out that in models with modular symmetries, the coefficients of the mass sum rule depend explicitly on the mixing parameters. An example is shown here, where we see that the coefficients f1 and f2 are functions of the model parameters theta and phi. Here I show then the predictions for the observable in neutrino stellar beta decay, MEE, over the lightest neutrino mass. In purple, this is the in the full purple region. This is the model prediction in normal ordering. This orange region, this is the model prediction for inverted ordering. And we see that for inverted ordering, only a very small region is predicted in these models. And for inverted ordering, also a very heavy absolute neutrino mass is predicted, whereas in normal ordering in this model, the lightest neutrino mass can go actually very close to 0. Looking at the other models we surveyed, we find that generally modular symmetries with which have mass sum rules predict large absolute neutrino masses. And these can be probed soon by cosmology. Then turning now to the final predictions, as the coefficients in the mass sum rule depend on the model parameters theta and phi, this also means that the mass sum rule depends on the mixing parameters in the PM&S matrix, such that we obtain now correlations between delta and the sum of the neutrino masses, which can be probed by cosmology. And this is what I show on this slide. The x-axis is the sum of the neutrino masses, the y-axis is delta, left is normal ordering, right is inverted ordering. And we see that only in sum rule 1, in model 1, which is represented by the blue region, the lightest allowed value of the sum of the neutrino masses can be achieved, and this can only be achieved if delta is equal to pi. This statement is less strong in sum rule 4, but also here we see that the lightest neutrino mass can only be achieved if delta is around pi.
You have 3 minutes.
Yeah, thanks. For inverted ordering, we see something similar. We see also again that sum rule 2 and 3 have very similar predictions, whereas sum rule 1 in blue and sum rule 4 in red have different predictions. And finally, I show the correlations between theta 2, 3 and the sum of the neutrino masses. Again, for sum rule 1, the lightest, the minimal value of the sum of the neutrino masses can only be achieved if theta 2, 3 is larger than maximal. And also for inverted ordering on the right, we see that for maximal theta 2, 3, which is sine squared theta 2, 3 equal to 1/2, we obtain similar sum of the neutrino masses larger than 0.17. So as there are correlations between the mixing parameters and the sum of the neutrino masses, there are very interesting and very unique synergies between long baseline experiments, which can measure the mixing angle, and experiments sensitive to the absolute neutrino mass scale, for example, cosmology. So let me come now to my conclusions. So future experiments will thoroughly probe the neutrino sector and will hence be able to test flavor symmetries. The predictions of leptonic sum roots can be used to plan different stages of experiments, can be used to identify the parameter space of interest, and can be used to identify the necessary precision needed to discriminate among different flavor models. So sum roots are an opportunity for model builders, phenomenologists, and experimentalists to gain more insights into the mysteries of the neutrino sector. Thank you very much for your attention.
Thank you. Thank you for the nice talk. Yeah, it's amazing. The result is unbelievable, I think. Do we have any question? No question? Julia, would you go back to your page 21?
Yes.
So here, so delta is kind of a CP violating phase, right?
Exactly, yes.
Okay, so if we accept this inverted hierarchy, right?
Yes.
Then, yeah, actually, then we do have a kind of a lower bound on the masses, right? Mass sum.
That's very true. Yes,
Yeah.
that's absolutely true. Yeah, that's of course very interesting. So for inverted ordering, also, as you can see here, the dashed lines, these are the current 3 sigma regions for delta, and you see that from the global fits. So that you see also that currently delta equal to pi is, for example, not favored by the global fits. So if delta equal to pi is actually observed, these modular symmetries cannot reproduce delta equal to pi. However, if any value between pi and probably 2 pi is observed, then modular symmetries can reproduce this value of delta, and then we also obtain at least a lower bound on the sum of the neutrino masses.
Okay, okay. So I'm sorry, but could you remind me of what this SR1 is, the blue one?
Yes.
Blue one.
Yeah, so this is so SR1 is just the abbreviation for a model we surveyed. This model is just based on certain symmetries. It's just one of our model benchmark points we looked at.
Okay, okay, I see. Okay. Okay, is there any other questions or comments? Okay, thanks again. Yeah, thank you. So our next speaker is Junichiro.
Hi, so can you hear me?
Kawamura.
Hello. Can you hear me?
Yeah, I can hear you.
Okay, so let me share the screen. So now can you see this, right?
Yeah, I can see. So your title is more than 4 muon signals, right? From vector-like leptons decaying nucleophilic G prime bosons at LHC. So do you want to cover the muon G-2 also, or?
Yes.
Okay, great. So then you have 15 minutes. So
thank you.
Please start.
Okay, so thank you for introduction. And so yeah, today I'm going to talk about a very distinctive signal predicted from models that can explain the mu anomalies. Okay, so and this talk is based on this paper we recently submitted and in collaboration with Stuart Levy. Okay, so you may know that there are some discrepancies in the physics related to muons. And one is the muon G-2, which is recently measured at the Frame Lab. And so now we know that the experimental value is deviated from the standard prediction by 4.2 sigma. And also we have some anomalies in the BTS mu processes. So for instance, this quantity RK is basically the ratio of the B2K mu over B2K EE. In the standard model, this value is predicted to be 1, but the experimental value is slightly closer to 1. And because now we have the pretty precise measurement, so now its discrepancy is 3.1 sigma. And the more interesting feature is that we have some discrepancies in other observables related to BTS MIME processes. And by combining them, we know that the new physics, with new physics contributions, we can explain the experimental results better, more than 5 sigma in the global fits. So this seems to be can be a evidence of the new physics. And interesting fact is that both can be related to the new physics related to muons. So it's nice if we can explain both of them simultaneously. And actually, we proposed that such a model and some simple extension of the standard model by introducing Z prime, U1, extra U1, and the vector families. And actually here, the vector lepton is important. So in this model, we can explain the muon G minus 2 by this diagram, where it's mediated by vector lepton and the Z prime. And we can explain that the muon G minus 2 if the Z prime mass is at 500 GB and the coupling is in this site, where the mean that coupling is order 0.1. And this model can also explain the BTS mu. And here, I didn't show the definition of C9, but this is a Wilson coefficient, this 4 Fermi operator. And the experimentally favored value is in the range of -1 to -0.5, roughly. And so this range of value can be explained again if the Z prime is at the 500 GB and the coupling has these sizes. So anyway, so in this type of models, we can explain the both anomalies simultaneously pretty easily. And if the masses of these new particles are over order 500 GB, and this mass range is, of course, a very good target at LC. So we would like to find some signal at LC, and that's the main topic of this talk. Okay, so you may concern about, as the first speaker, first talk of this session, we should consider the Z prime search because this often gives a very strong constraint. And for our case, the dimuon search may give the very strong constraints because of this Z prime production to dimuons. And so here the typical constraints. So if the Z prime boson decays like the boson, if in such a case the limit is very strong and it's about 5 dB. So the 500 GB may be excluded, but in our case, interestingly, so the consistency with anomalies and also the BSBS by missing measurement, the co-coupling is predictively small. So here again, this is a formula for the C9. And now let me remind you that the typical value of the cork to the strange cork and bottom cork is of this size. If we assume that the Z prime coupling to the mu is of the 0.6, which is naturally expected from the explanation for the muon G minus 2. And the small this SB coupling is favored to explain the neural discrepancies in the BSBS by mixing. So we showed that this Z prime constraint is can be avoided due to this small coupling with corks. So the production cross-section is very suppressed, even though we have the light Z prime, so that we can have this fiduciary cross-sections can be smaller than 1 femtobarn, which is much smaller than the current experimental band. So in some parameter space, we can evade the Z prime search. And so let me discuss about our main topic of the very distinctive signal of the modern field muons. So we consider the vector lepton production, and it will decay to Z prime and the leptons. So here we assume that the Z prime is larger than the vector leptons. And so in such a case, if the both Z prime will decay to dimuons, then we actually have the 6 muons. So here, so one vector electron can produce the 3 muons, and since it's pair produced, we have at most 6 muons. But of course, Z prime could decay to neutrinos because of the SU2 symmetry. Z prime may also couple to neutrinos through the left current interactions. So in such a case, and if the one of the Z prime decays to neutrinos, we only have 4 muons. And furthermore, we may have the vector neutrinos as a SU2 partner, and its production may have the 4 muon signal. So in many cases, this model predicts the 4 muon signal, and at most the 6 muons from the pair production of the vector lepton. So this must be a very nice signal because the signal background is very low. So this is a very good golden channel to search for this kind of particles. can explain the anomalies. Okay, so but in the later analysis, we assume that these things. One is that the vector lepton is a situated singlet or doublet-like. So here the production cross-section is given by here. And so we will further assume that the vector neutrino has the same mass as the charged vector lepton for the doublet case. And of course, in the singlet case, we don't have the vector neutrino. And the further more important assumption is that Z prime only decays to muon or neutrino. And so we neglect the Z prime decays to quarks or other particles because as I explained, the Z prime couplings to quarks should be small to evade the LHC band, also to explain the anomalies. So that we assume that the Z prime dominantly decay to muon or neutrino. And further, we assume that the Z prime coupling to the muons in left current and right current are the same. In this case, the branching fraction is 2/3. And this assumption is justified when we consider C9 only or C10 only scenario to explain the BTS anomalies. And so here is our assumption in the later analysis. And so what we did was recasting the Atlas analysis recently proposed. So we basically recasted this experimental data. So actually this Atlas analysis is looking for the alpha-parity binding supersymmetry, which generates more than 4 muons. And thus here I show some most relevant signal regions we discussed. And so the first two signal region require that more than 4 muons, 4 leptons. And important cut is the zeta boson veto, which means that the lepton pair should not have the invariant mass near the Z boson mass. So these are events with this Z boson-like lepton pair is vetoed. And also they further require that the effective mass should be larger than 600 GeV in the loose region, and should be larger than 1.25 GeV for the tight region. So where the M effectives define the mass of the sum of the missing VT plus the PT of the leptons and jets. Also, our signal doesn't have the jets. Okay, so in addition to them, they also consider the signal region with more than 5 leptons, and no further cuts are required. So yeah, we basically studied these signal regions. And here's the experimental result. Unfortunately, we don't have the very significant excess above the standard backgrounds, but a bit interestingly, we have some excess in the one signal region requiring the more than 5 leptons. Also, this is just 1.9 sigma, but as I said, our model predicts more than 6 muon signals, so we can quite easily, we may be able to explain this excess. So it's worth studying whether we can explain this excess. So I shall discuss about this later. Okay, so here is our current limits on the branching fraction of the vector lepton to Z prime here. So another important parameter is the branching fraction of the vector lepton. And so we put the upper bound on this branching fraction. The left panel shows the bands on the singlet-like vector lepton case. And if we assume that the branching fraction is 1, so in this case, the limit is at 1 TeV. And for the situated doublet case, because of the larger production cross-section, the limit is about 1.3 TeV. This looks very strong in spite of it's just electric particle. And of course, if the branching fraction is smaller, then the limit is weaker. So for instance, if branching fraction is about 0.6 or 0.7, the limit is about 750 GeV. Also, this is still strong. And I note that the limit from the signal region requiring more than 5 leptons are much weaker because of the excess. And also, the other model predicts that many process predicts only 4 muons. Okay, so let me discuss about the explanation for the excess in the more than 5 leptons signal region. The problem here is that we should explain the null excess in the other signal regions requiring just more than 4 leptons. So, but in this signal region, the difference from this signal region is that they require some M effective cut, and so the M effective distribution is very important. So that, as naively expected, if the vector lepton is heavier, then this M effective distribution tend to be higher. So here, the red histogram shows the case of the vector lepton mass of the 1 TeV. But if it's lighter, so its distribution goes to light region. So this histogram is given by this green histogram. So to evade the some constraints from the other signal regions, actually the lighter vector electrons are favored. And so actually, if the vector electron is lighter, we can explain the excess consistently with the other signal regions. So here, the right plot shows the MF missing ET distribution. In the case of the branching fraction of D prime to E mu is the 0.25. So in this case, this plot shows the histogram or distribution of the missing ET. And so the yellow histogram bins show the some of the backgrounds, and the black dots are the data. So we have some excess in these bins, and we can nicely explain this excess by our new physics contribution by the vector electron production. And we checked that, of course, the signal events in the other signal regions are sufficiently small, smaller than the current upper bound. So now we can explain the excess, but I should note that our model only predicts the muons. So, but their excess may also include the electrons. In such a case, that we cannot explain the excess. But actually, unfortunately, we couldn't find any flavor information from the experimental paper. So we just comment on that. But we could explain the excess if they are dominated by the muons. Okay, so before closing my talk, let me discuss about future limits at the higher LHC. This is just a very rough estimate. But so the left panel shows the future sensitivity for the doublet vector electron case from the tight V vector case. So this we just rescaled their already defined signal region. And so now we see that in the future experiment, if the branching fraction is 1, the limit is about 1.7 TeV. And also the white line shows the upper bounds on the discovery potential. So if the branching fraction is 1, we can discover these signals up to 1.5 TeV. And I should note that the parameter space where we can explain the excess is around here. So this is completely covered by the higher luminary LHC, and even we can discover them. And also, of course, this signal region is not very optimized for our scenario. So for instance, we have the Z prime, which decays to the dimuons, which have the resonant structure. So it would be nice to further require the cut like opposite sign invariant match should be close to some higher value, like 500 GB in this case. And in this case, we have more good sensitivity in these regions by this requirement. So we may have better sensitivity by requiring these kind of cuts. So we propose this kind of new cuts to search for our scenario. Also, this is a very rough estimate, but we expect we have much more better sensitivity if we require these kind of cuts. Okay, so let me summarize. So we propose the possibility that we may have more than 4 million signals from the model extended by the vector electron and Z prime, which are strongly coupled to the muons. And this model is very motivated to explain the anomalies. And we show that the current limit is more than 1 TeV if the branching fraction is close to 1. And the future sensitivity at the higher LHC is about 1.2 TeV for the singlet-like case. And for the doublet-like case, the limit will be much stronger. And also, we discussed whether we can explain the excess in the more than 5 electron signals, and we showed that we can explain if the mass range of the new particles is at 400 GeV. But I should note that the flavor information is very important, and our model basically only explains the muons. So to test, in general, so to test this kind of muon anomaly explanation, the flavor information is very important. So it would be nice to know whether these signals contain the electron or muon. Okay, so that's all. So thank you for attention.
Thank you. Thank you for the nice talk.
Thank you.
So is there any question or comment?
Excuse me?
Yes.
May I have a question? This is Ziting Liu from KIAS. So I have 2 questions for your talk, for your nice talk. So the first one is, in your model, you have a vector-like lepton E. So my question is, this E is the flavor dependent or flavor independent? And the second question is, for your Z prime is a muon-philic. So in general, this kind of muon-philic Z prime is not anomaly free. So what kind of gauge U1 do you use? And
Yeah.
what kind of the charge assignment do you use? Thank you.
Yeah.
I had the same question. So
okay.
yeah.
Yeah. So for the first question, so yeah, we assume that the vector lepton dominantly couples to lepton. So of course, to avoid such constraints from flavor violation, it should not couple to electron. So yeah, we basically assume that it only couples to muon.
Okay.
For some reason. Yeah. So it's a completely flavor dependent. Okay.
Yes.
And so for the second question, so yeah, we assume, so we put the U1 charges only to vector-like families. And so, yeah, and only the vector-like families. And so in our model, so we also introduced the U1 prime breaking Higgs field. So after the symmetry breaking, there's a mixing between the standard generation and the vector-like generation. So after the mixing, so there are some coupling with the vector lepton to some of the particles, or the Z prime to lepton couplings are introduced. Okay. So we can put assign the U1 charges only to vector families in the gauge basis in some sense. Yeah.
I have a question.
Okay. Yeah.
So it's a nice presentation. So my question is about tau sector. Although you may not couple to tau sector.
Yeah, we assume so.
Can you comment on suppose the tau coupling is turned on, it may be less stringent than the coupling for electron. So
yeah, that's right.
Have you thought about that, turning on tau coupling?
Yeah, actually, in our paper, we also turned on all the couplings and try to. So we also discussed about some flavor violation patterns, also in the pointers mutant gamma, or also the tau e gamma, tau mu gamma.
Because as I remember, many people, including myself, consider L mu minus L tau model. In that case, there was some strong bound from tau decays and also neutrino trident production. So the G minus 2 region actually was ruled out in that case. So, but I think your model is different. So
so our model is different. Yeah. So maybe good or bad point of this model is that we can completely control the couplings. So we can even just forbid the coupling to tau, which can be 0, so not excluded. Yeah, we can freely control. So this is in some sense a good point of this model. We can quite easily explain that.
You could allow for small but sizable coupling to tau.
Yeah, that's
that
true.
You can probe it in the future. Although
so we can turn on that, and that's right. So in model can have flavor variation involving tau. That's possible.
Okay, thank you.
Okay, I think we should stop here, and I thank the speaker again.
Thank you.
So let's move on. Okay, and
yes, hi.
Hello.
Hello. I share my screen now.
Okay. How should I pronounce your name?
It's Fagner.
Okay, great.
Yeah. So I suppose you can all see my screen now?
Yeah, I can see your screen.
Okay, good.
So you have 15 minutes?
Okay, thank you.
Yeah.
Okay, I will start. Good morning. Good morning, everyone, and thank you for the chance of having your attention to this topic. So I will discuss about how to probe leptophobic abelian extensions of the standard model at the J-Park Koto experiment. This was work made in collaboration with Professor Pianko and Dr. Seon Bak, Chen Yu, and Yu Jomura, and was developed at KIAS. So this is the outlook of my talk. So the recent results provided by the Koto experiment, sorry?
Would you go to the full screen so that we can see?
Okay.
Full screen, yeah.
Full screen, yeah. How is here? Okay.
Okay, better. Thank you.
Okay. Thank you. Sorry for that. Okay, so the recent results provided by the Koto experiment did not improve the most stringent limit in the k-long to pi and missing mass channel. And this limit is such that a considerable room for new physics is still allowed if compared to the standard model prediction. So the idea of this work is to study this room from k-long decaying into inelastic scalars, which already has been the topic of some talks in the PASCOS, where the heavier component of the scalar further decays into the lighter component plus pi 0. You can study the same process now with fermions instead, where a massive neutrino decays into active neutrinos plus pi 0, and also light vector. The light vector is produced and further produced on a shell and further decays into a neutrino pair. So we know that typical ways to study new physics, to study physics beyond standard model, is by either changing its scalar spectra, adding new fields to its scalar spectra, or either deforming or adding a new gauge symmetry to its gauge group. So here we do both. We do both with the most canonical examples that we have in the literature. One is the 2-ADDM, and the other one is the abelian extension of the standard model. So the idea is to generate these two operators that we can use to describe the Koto physics. One is this second example here. So we have the bilinear of both chiralities coupled to the missing mass current in the vector case and similarly to the scalar case. So these operators, they can be induced when the standard model fermions are chiral under this new abelian symmetry that we introduce. So, and typically, if once the standard model fields are chiral, that would request at least a second Higgs doublet to its scalar spectrum. In this sense, chiral U1s are somehow also connected to the 2-ADDM models. So, and as usual, to introduce a new gauge group, we should be able to accomplish at least two criteria. One is that the model should be anomaly free, and this is typically done by introducing also new chiral fermions there, and it should reproduce the mixing matrices that the standard model, that is well known from the standard model. That means it should admit renormalizable Yukawa couplings to all the standard model fermions. These are two necessary conditions to write any possible new physics model UV complete. And in our case, so since, as I said, in order to accomplish the first criteria, that is, the model should be anomaly free, we are also free to add a totally arbitrary new physics content, like exotic sector of our model. And how we do it, we basically ask that at least for one of the models that we will provide, we should be able to reproduce the standard model times U1 breaking pattern, following the breaking pattern of the E6 theory. Okay, so we know that one of the steps of the breaking pattern of the E6 is standard model times U1. So we need our content to be able to be complete in the E6 version. Okay, so at least in one of them. And what does that mean? That means that we should add SU2 neutral lepton singlets. We call this NR and NL. A pair of quark singlets, this is the LDR, and lepton doublets, LL and LR. So the H charges, I call H charges the charges of this new U1, and then this index H here is by the fact that the second Higgs doublet is charged under this new U1 as well. So the H charges constrain the Yukawa interactions to be those of a type 2 to ADDM. Okay, and so this is the criteria that we follow to raise our models. And the model should be leptophobic over the standard model leptons. So by following this, we find this solution, this set of solutions we have here. So the first table is the standard model content plus right-handed neutrinos, right? And so here we have the known charges of the standard model gauge group component of this. Of our larger theory, and then here the U1H charges, and here the exotic sector that we have. What we may notice here, and what we must notice here actually, is that we have this parameter which is called B, which is arbitrary again. It's just a scaling factor, so it does not have any physical effect. And we have this parameter A, which is actually the parameter that allows us to distinguish between two different models. And why? Because what is physical in this charges is the ratio between the charges of two different Fermi representations. Right? So just remember that then we have this parameter A that defines a specific model. And more than that, I will come to this later in the end of the talk, that we notice that if you just define this B as 1 over 1 plus A, all models here, they would generate, all processes in all models where the content is only the standard model content, they are equivalent. So right, we see that here, if B is 1 over 1 plus A, this is 1, this is minus 2, and this is 1. That means that the standard model charges does not change for all models, right? And this is important because this is a way for us to constrain all models at once by just selecting processes where both external and internal fields, external fields and mediators are in the standard model sector. Okay, and we'll explore this later on. Okay, so just a very brief discussion about how the gauge sector changes in this theory. So the covariant derivative gets now the contribution of this new vector, and the coupling with the Z, all the gauge couplings now is affected by a new mass mixing effect, which is measured by this theta angle here. where GZ is the usual standard model given by this formula. So we see that as theta is supposed to be a small parameter, right? So such that the couplings between Z and the standard model formulas are not disturbed too much. Okay, so as theta is a small parameter of the theory. In the decoupling limit, where ZH is actually the couple of the process at the electric scale, we have that this mass mixing angle it scales with 1 over the mc squared over the new vector mass squared. That means that in the limit, we can actually assume that the theory is totally leptophobic, but only in the limit where ZH is heavy, because when ZH is light, so this mixing angle scales with this delta here, which goes the gauge coupling. That means that essentially we cannot neglect the contributions from the mass mixing, even though the theory is leptophobic for process where leptons are involved anyhow. So, and then we select one very specific model, which is, we chose that parameter A is equal to -6, and that implies this subset of our Lagrangian. That is one operator here related to neutrino masses, one here, which is just a bare mass term, which actually induces a type 1 seesaw as known. Also a term here of a broken standard model singlet scalar, right, which is called phi 2, which will mix these two singlets here and also contribute to the hierarchy we need for the neutrino masses.
Excuse me,
please.
you have 3 minutes?
I have 3?
3 minutes.
3 minutes. Okay, so I will hurry then. I thought, okay. Okay, so this is the content that we have. We have a dark matter candidate here. We have neutrino masses, and then we introduce a new inelastic singlet here in order to study inelastic scalars in the Koto process. I will just, this is the main point of the talk, that is, rare processes are typically related with flavor changing vertices. In universal theories, so flavor changing neutral currents at tree level comes only from mixing between the standard model and new physics. If the new physics sector is dark, that means that this mixing is forbidden, and therefore that FC and C would start to show up only at the loop level. That means that when you have universal theories and your neurophysics sector is dark, the physics of the portals would show up only at the quantum level, okay? And therefore we need to generalize our penguins, which is we need to compute all of these diagrams here for both the ZH and to the scalar mediators. So then again, I will just mention that, remember, we have both 2ADDM and U1. We can test the features of both models simultaneously in this setup by just switching on and off all of their contributions. So we can test 2ADDM, U1X, or 2ADDM plus U1X at this. Okay, at the electric scale, the theory would rely on the presence of a light scalar among its spectra if this new singlet is a dark matter candidate. And if it is mediated by a light scalar, this process would already be p-wave, and then therefore safe from CMB bounds. We see here this red band and this green band here, the Koto bands. That means that in the electric region, the Koto is actually very competitive with bounds provided by collider searches of charged Higgs. And in the light case, again, we have one example here where the Koto region is competitive with Babar, which does not entirely overlap with our setup, but still mainly in the scalar case and not in the fermionic case. Okay, so okay, now again, okay, I will move directly for this correlation plot. And between, I said that the same contribution could be seen in the K plus the case to pi plus in E. And therefore, it's important to see the correlation between these two branching ratios here. So we see that here we move for 500 MeV, the mass of this vector, this new vector, up to the 1 GeV, and we see that we have one region here where it is in the allowed room for new physics for both K log and K plus, but therefore it leaves, and later on in the same interval, it leaves the allowed region here, okay? And as I said, we can use our setup to constrain all sort of all models in this framework by choosing one processes where only standard model fields are involved, and BS to me plus me minus is one of this. That means that these bounds here for the gauge coupling these bounds here are present all models that we have selected, okay? And why? Because only standard model contributes to this. Just to conclude, a small comment about dark matter in this. Inelastic scalars have been a topic of discussion in the community recently, and how about the assumption if these dark scalars are dark matter or not? So we know that for the light scalars, that means they should be present in the K long decays. We would need the annihilation channel of controlling the abundance of these fields to be in the P wave or P wave dominated. That it is true if the axial components are 0 or negligible, or if the splitting between the mass of these fields are small enough, okay? Both cases we cannot have in Z prime mediated process. And why? Because we need the mass splitting to be such that we can produce a pion, and that already makes the theory, this assumption excluded. And we have Z prime, therefore, it's not a dark photon, it's a Z prime, therefore axial vector couplings are present there. And how to solve this? So Z prime cannot be the main mediator controlling the abundance of these scalars, and therefore we would need a light mediator would be a scalar to be resonant and controlling the annihilation channel of the scalars, and which is already P wave. Therefore, the presence of resonant scalar mediators in this hypothesis is necessary. So to conclude, we have provided a class of type 2 DDM, which is embedded in a leptophobic abelian theory and is supplied by a dark sector. We provided generalized formulas for the loop corrected flavor changing vertex. And we probe the physics of vector and pseudoscalar particles for one dark matter model at the J-Parkoto experiment, which resulted in competitive bounds compared to both searches in the light or at the electric sector. Thank you.
Thank you. Okay, because time is up, so we can have about only one question. Is there any question? Okay. Okay, I'll ask several questions, but
please.
do that later via email or something like that. So let's move on.
Okay.
So would you stop sharing?
Yes.
Okay. Our final speaker is Dr. Chi-Ting Liu in KIAS. Chi-Ting?
Yes,
yeah.
Can you hear me?
Yeah, I can hear you and I can see your screen.
Okay,
so,
let me make a full screen mode.
Okay. Okay, good. So please start.
Okay, thank you. This is Chitin Lu from Kias, and today I hope to tell you a story how to connect the dark matter physics with a recent muon Gmi2 and assays from the Higgs exotic decay measurement in Atlas. And this story is based on this work. Okay, so in this talk, I will first give you a motivation and show the renormalizable simplified dark matter model in this study and the related experimental constraint and the main parts of result. And finally, I will give a conclusion. So as we know, the dark matter is very important questions. Even we already have many evidence for dark matter from the gravitational interactions, like it's really abundant and the rotational curve of galaxy and also bullet cluster. However, there are still many open problems. For example, the dark matter nature and interactions and the dark matter formation mechanisms. And hopefully, we already have many detection techniques. For example, the Collider search, the dark matter detections, and also the indirect detection from the annihilation product like the neutrinos, antiproton, and gamma ray. So like this cartoon, we have three different directions to search for the dark matter, especially for the dark matter detection. It's already give us very strong bound. So some people try to think if the weakly interacting massive particle WIMP is still alive or dead. And some of them try to consider different kind of mechanisms of dark matters. So this is first problem. So is a WIMP still interesting? And if we can have other search ways for this kind of WIMP diameters. Another issue is about muon Gmi2. I think I don't need to say too much about this exciting result. This 4.2 sigma significant deviation from the cinema prediction. Actually, it's make many people propose different kind of BSM explanation overnight. So people try to propose different kind of new physics inside this loop. However, we still need to be careful. Maybe a detailed study for the lattice QCD results can help us to make sure it's really come from the BSM physics or it's still consistent with the standard models. Anyway, it's a quite interesting result from here. So we can propose as many as possible new physics explanation. And then this one, maybe some people not familiar with. Recently, the Atlas Higgs boson exotic decay search, they also find an axis. And in this study, they consider the Higgs boson decay to light scalar A and decay to 2B and 2 mu in this mass range. Actually, this decay channel is a golden channel because the in this mass range, the small a decay to BB bar have a large branching ratio. On the other hand, a decay to mu plus, mu minus can be a good triggers, and we can have a very clear reconstruction resonance for these A particles. And they have a very interesting result. They found around the mass about MA equal to 52 GeV. There's a local axis about 3.3 sigma here. Unfortunately, the global just 1.7, so we still need more data to confirm this is a new particle or not. So in this talk, I hope to combine them together. So we try to use simplified dark matter models, and here we have some freedom could choose what kind of dark matter could be. And in this study, we simply choose it at the Dirac fermion chi. And for this simplified dark matter models, we choose the mediator as a A0. And we use this A0 to explain the axis of this Higgs exotic decay about 3.3 local acids with Ma mass equal to 52 GeV. And this A0 is a pseudoscalar, and because of this nature, so it can be highly suppressed in the tree-level diameter and nuclear scattering. So it can easier escape from the constraint from the recent diameter degradations. So this is good. So this kind of scenario is still alive. And on the other hand, we also try to explain the muon GMI2 measurement. Mainly come from these one-loop diagrams. And I will show you later, in this model, we also introduce a fetter-like muon lepton. So this fetter-like lepton is a muon-like. And actually this psi I is very important, not only contribute to the one-loop muon GMI2, but also for this Higgs exotic decay. And I will show you more about why it's also important here. And let me briefly introduce this renormalizable simplified diameter models. And this model is based on these two work. And the first part is about the diameter interactions, then for the interaction for the mediator. And here I highlight two terms, the dimensional 3 mu A and mu A prime terms. And this term will break the parities. So you can imagine we have the CP violation in the scalar potential. And after the spontaneous symmetry breaking, the small a and capital A will form the mass eigenstate H0 and A0. And similarly, this fetter-like muon lepton and muon will mix together after EWSB. And because of the precision measurement of Z boson to the lepton pair, this coupling kappa here already suffered from a very strong constraint. For example, if the M psi around the electroweak scale, then this kappa need to be smaller than 0.01. Okay, here are this the all undetermined parameters in these models. They are in total 10, and actually 3 of them are not so relevant in this study. So we fix them to these 3 values, and we do the parameter scan for the other 7 free parameters in the following range. And here for the experimental constraints, we first focus on the muon GMI2 delta A mu. We try to fix our parameters to agree with this range. And this delta A mu is mainly come from these one-loop diagrams for this formula showing here. And the second part is we try to fix our parameters space to agree with the ethers Higgs boson exotic decay axis for this one. And we can explain this one as the branching ratio of H0 to A0, A0, and to 2B, 2 mu around this value, 3.5 times 10 to the minus 4. And there's a very interesting things here. So if we just try to explain this A0 to be standard model singlet scalar or one of the scalar or pseudoscalar in 2HDMS, actually it's not so easy, it's very challenging to explain this axis. We need something extra. For example, here in our models, after the spontaneous symmetry breaking, this psi L can mix with the standard model muons. So it will modify the particle A decay to mu plus, mu minus, such that the branching ratio of A0 to mu plus, mu minus will enhance, and we can more easier to fit this branching ratio, even we involve the constraint from the Higgs exotic decay need to less than 19%. There are also other constraints, for example, from the LHC Higgs boson measurement, we involve the Higgs boson exotic in invisible decay less than 90% and 9%. And also because it will modify the standard model coupled to the mu plus, mu minus as well. So we also involve this constraint. And the psi plus minus will also modify the H0 decay to diphotons. So we also involve this one. And for the diameter phenomenology, so we consider the diameter rate density and diameter directions. So as I mentioned before, thanks for the pseudo-scalar nature of the mediator, actually their contribute to the direction is very small, and we can safely ignore the constraint from diameter direction. And then as the Kawamura's talk, so the Atlas multi-muon search is quite important and may give us very strong constraints in our scenario as well. So from this SUSY search, they consider 4 or more than 4 charged leptons in their case. And in our work, we also try to recasting this result in our models. And in our models, the major production mode is the pair production of the this vector-like muon leptons, mu plus, mu minus pair. And we focus on the recasting for this signal region of more than 5 leptons as the Kawamura's talk. And actually, you can see in this parameter space, it already gives us very strong constraint in our parameter space. And here, our signal is the 6 muon in the final state. So unfortunately, unlike previous speakers' result, there's a muon-philic Z prime. Here, our A0 cannot be muon-philic. So the coupling can enhance the A0 to mu plus, mu minus, but not so much because of this strong constraint.
Okay, so
thank you. I see. So we also have the, because as I say, we have the H and A CP violation interactions. So this model also suffered from the EDN constraint of electron and muons. So let me show you some results. So for example, the one relevant to the muon G-2 muons give us the constraint of the kappa prime. Let me show you the kappa prime is these interactions. Need to be a 1.8, and the mass of the vector-like lepton, muon leptons need to be less than 315 GeV. And you can also show in this parameter space, actually the new combined result from Fermilab largely shrink the allowed parameter space. On the other hand, is for the constraint for the Higgs measurement. The allowed parameter space show the missing angle should be less than 0.15, and the coupling between the Higgs and 2A, two pseudo-slate like A, should be less than 0.01. And we can also explain the Booth result to the branching ratio of A0 to BB bar and A0 to mu plus, mu minus in order to explain the Atlas Higgs exotic decay axis. So we find the A0 will still majorly decay to the BB bar, and its branching ratio need to be larger than 85%. And last but not least, actually the diameter indirect detection is very interesting in our models. So for the crustaceans, the left-hand side, we already familiar with this one, is come from the Higgs funnels around the Higgs boson resonance peak. And for the A0 area final state or BB bar final state, and here we also show you the gamma ray data for the final state for mu plus, mu minus, and BB bar final state. So for the Higgs funnel region is still far from this constraint. However, in our model, we have a very interesting cascade decay channels from the diameter annihilations. So for diameter annihilation, they will produce a mu and psi, and psi will keep decay to BB bar and mu. So it's a full body decay in the final stage. So we still need to have a more carefully analysis for this kind of full body final state. And maybe after a very carefully study of this one, it will show us the dictation may also already give us very strong constraint or not. So in the end, so in this talk, I hope to show you a simplified diameter models. It's a WIMP diameter model and it's still live and still interesting and can explain some acids like the muon G-2 and also the Atlas Higgs exalt decay acids. And they also predict some very interesting signature can be searched on the collider and also for diameter interpretation. Also, thank you for your attention.
Thank you. Thank you for the nice talk. Okay, so do you have any question?
Can I ask you a question?
Yeah,
Oh,
please.
sure. Shinichiro.
So you're from your vector lepton pair production, phi A field may dominantly decay to BB bar, right?
Yeah, sure.
So is there any constraint from that decay channel? I mean, from
actually,
lepton production.
Yes, for the A0 decay to BB bar, because of a very huge QCD background, so the constraint is still weak.
Okay. Even though, okay, sure. For
right, we also, yes, we also check as you say, the constraint for the Higgs decay to AA and to 4B. But unfortunately, this constraint is still weak.
Yeah, but so if we consider the production from vector leptons, so we also have two muons already.
Yes, you're right. Let's see.
Even though, so we have basically four bottoms and two muons.
Yes, you are right. For example, here the phi plus minus to mu plus minus to A, then A decay to BB bar.
Yeah.
This is also possible. Exactly. But unfortunately, for a reason, both Atlas and CMS search is not give us very strong enough constraint for our model. But in the future, yes, right.
Okay. So did you give a comment also for just 4 muons? I thought that that may give a stronger constraint than the 5 lepton signal region.
Yeah. No, in our case, because how to say, in our models, they will have a 6 muon in the final state. And of course, we can reconstruct, for example, the A0 decay to mu plus, mu minus, and A0 decay to, for example, BB bar or others. Then they will have 4 muons, right? But once we involve the other constraints, when we do the recastings, then because of other constraints, this is not as strong as this 5 lepton constraints.
Okay, so you say this gives
this one,
strongest
this one is
constraint.
the strongest constraint. Yes.
Okay, thank you.
Okay, I'll have a question.
Yes, please.
Cheating. So I don't understand how your A couples to B quarks. You said A decays into BB bar.
Yes.
Well, but you introduced a kind of a vector-like lepton, right?
Yes. So first of all,
the mixing.
Yes. So first of all, this standard model Higgs and A capital A have the mixing.
But A, so is I thought A is a pseudoscalar.
Yes. So there's a CP violation.
CP violation
in a scalar potential, but hopefully, let me show you more detail in the Lagrangian. So here is very interesting. So you can find, so for the diameter sectors, they're only gamma 5 interaction. And in the standard model sector, if we ignore the muon part, they are only scalar interactions.
Okay.
Yeah. And the more interesting is for the muon parts, they have a CP violation for the all scalar and pseudo-scalar interaction. So this is a more dangerous part. So the BB bars come from this missing interactions.
I see. So, okay. I'll ask other questions later. Okay.
Yes, please.
So time is up. Let's thank the last speaker.
Thanks a lot.
Thanks a lot. So I'd like to thank all of you and see you soon in the afternoon. Thank you.
Thank you. Bye.
Bye-bye.